and scale-free networks in this. In fact, it will require like 6-7 hours to yes. And in brief over important complex networks metrics, and I'll introduce random networks here. Before going for small well and scale. So what we see now on the screen is a set of examples of real world networks. This is a social network where people are captured in the form of a network or a graph. And what we see here is a road network of Bangalore city where intersections and the road segments make the network as a graph. Power grid network formed by the power distribution, generation, and events of the network of our country. This was a biological network formed by the relationship between the biological elements within our body. Now, there are many such real-world networks that exist. So, a network is nothing but a complex interlock system which can be a representative of the real world. And a complex network is a network for a graph which is non-linear topology. So, what that non-linear topology means, it's not easy to describe. It's complex that we cannot easily describe that. Now, as I mentioned, in any network, we have certain entities that are represented as nodes.
Excuse me, sir. Sir?
Yes.
Sir?
Yes.
Sir, voice is breaking, sir.
So, can I stop my video so I can?
Yes, sir.
Now, as I mentioned, that any network has a set of entities represented as nodes, and their interactions or the interaction between the entities are captured as links. So these nodes as well as links together form the network. Now, to recollect once again that many of the real world systems can be modeled as a network. For example, the communication network, the transportation network. Many of the technological systems can be represented as network, the internet, and many more. So this is actually giving a new way of analyzing some of the physical systems to get an idea of how the physical systems are characterized. Now, I want to briefly explain some of the metrics with which networks are typically characterized. So, average diagonal degree, average clustering coefficient, average path length, network diameter, average edge length, degree distribution, central symmetry, and the degree distortion. A few of them I'll go with examples just to give you a glimpse of what these metrics are and how they actually are used for characterizing the network. So, average neighbor degree of a graph is nothing but the summation of the degrees of individual nodes divided by the number of nodes. So, this is a very small network. You can see that for this particular node V1, there are 3 neighbors. So, 3 is a neighbor degree for this node. For the node V5, there are 4 neighbors. 4 is a neighbor degree, and V6 has 2 neighbors. So, if you sum up these degrees of individual nodes divided with the number of nodes, we get the average neighbor degree, that is 3.3. So later you will see that in some literature, average neighbor degree also is represented as degree centrality, particularly in the report workflow. Well, any questions? Okay. Now, second very important metric that is widely used in studying the network is called the average clustering coefficient. So this is measuring how many neighbors of the node are collected. So if you are a node and you have certain neighbors, and the average clustering coefficient of you or clustering coefficient of you can be used to say how well your neighbors are connected. So now the expression is like a summation of the edges of your neighborhood, given all the neighbors within the graph, as well as edges within the edge set of the network, divided by the maximum number of possibilities among the neighborhood connectivity. And that is divided with 1 by N to get the average across the entire network. So let's just show one simple example to get this idea. So take the node V1 here. V1 has 3 neighbors, and the maximum number of connectivity among these neighbors can be 3 into 3 minus 1 by 2, that is 3. Okay. Now, however, this neighbor and V2 are connected only by 2 edges. So there is between V5 and V2, and there is another edge between V4 and V5. So you can say 2 edges exist between the neighborhood of V1, but there can be a maximum of 3 edges. So that way, the clustering coefficient of V1 is actually 2 by. And now consider node V6. V6 has 2 neighbors, and these 2 neighbors can have a maximum of 1 edge, one undirected edge. So you can have 1 over 1. You will have clustering coefficient 1. So what that means is neighbors are well connected. Even if this node V6 is not functional, the neighbors are not affected at all. So clustering coefficient gives a concept of neighborhood robustness. The failure of one node may not affect the neighborhood at all in the form of communication possibility among themselves. So once we get the individual clustering coefficients for each node, you sum it up, divide with the number of nodes to get the average. So this for this small network, the average clustering coefficient is 0.67. Higher the clustering coefficient, higher the local robustness of the network. Lower the clustering coefficient, lower is robustness. So the reliability, availability, and other issues of the network can be affected in the network. Now, third metric, which is a very simple metric but very powerful metric, is called average path length. So what this metric refers to is summation of the shortest path length of all pairs divided by number of possible pairs. So sigma I Dij, sigma Dij referring to the shortest path length between I and j, summed up in pairs divided by the number of possible paths. So we can see that if the metric is actually showing the cost between node pairs ij, say node pair V1 to V3, say V1 to V3, 2 hop path. So the cost is actually 2 hops in terms of number of hops, the shortest path, that is 2. So that is to represent the shortest path metric for every node pair, that is summed up and divided by the number of pairs that you get the average path length. So for this particular network, the average path length is 1.23 hops in the network. So higher the average path length, bigger the network. Lower the average path length, smaller the network. So given the average path length, the network diameter tells you what is the largest value of possible shortest path distance. So if you have a network diameter that is high, then we can see at least one shortest path existing as high as the network diameter value. Now, when you have physical network like road as well as telecommunication networks where the edge length matters, then average edge length is another metric that is used to capture some of the characteristics of the network. Now, it measures the ratio of sum of the lengths of each edge to a total number of edges. So, in this network, if we assume that every link is 1 unit, there are 4 links divided by 4 possible. Length is 4 for each length is each unit is each link has a unit length of 1. There are 4 links, you get the average edge length of 1. But suppose if you modify the network by adding a link between node 1 and 4, roughly the newly added long link will take about 3 units. So you can find that the average edge length now increases from the prior one to the current 1.4. So the edge length increases in such a modification of the network. Metrics that you have just seen, say average library degree, average path length, average clustering coefficient, network diameter, and average edge length, degree distribution is actually a significant. We will see a few degree distributions when we discuss the network. So basically the degree distribution is nothing but the probability distribution of the node and degree or neighbor degree over the entire network, and how they are distributed within the network. So this is a graph that can represent the degree of a node versus probability of finding certain number of nodes within the network to the same degree. Okay. When we discuss about small band and CHP network, I'll come back to degree distribution to explain how these are actually going to play a major role there. Now, further, I just want to introduce this metric called node centrality. Node centrality. So, centrality is a word used to represent importance of the network. Okay, who is central to the network? Who is more powerful within the network? And a few important centralities are here: degree centrality, cluster centrality, and between centrality. So let's take a couple of minutes to understand what is the meaning of this centrality. Now, so you may use many centralities to identify important nodes and there is no single centrality that can give a solution for all such estimation node importance estimation problems. Now, degree centrality, as I mentioned here, it is nothing but average library degree, but sometimes the weight of the edges will be added to it. For example, this is a small network where the topology is such that there may be a certain single node that becomes more important. So, for example, the node C here is actually having degree centrality very high, and so that node becomes very important node in this network. Now, this example doesn't show the edge weights, but in case if the edges are having edge weight, then this Gij, that is the degree of the node, will have a product with the edge weight of that. So, another centrality that is really important is called the closeness centrality. So, the closeness centrality measures how close one node is to other nodes in the network. Now, closeness centrality of a single node I can be obtained by estimating 1 over sigma j 1 through n dij, where the denominator parameter factor here sigma I, so sigma j 1 through n dij is nothing but the shortest path distances from node I to every other node in the network. So this is nothing but summation of shortest path from that node to every other node in the network, inversing that. So if you shorten the shortest path distances from a given node, this quantity CC will become higher. So higher the CC value, the closer a given node to every other node in the network. So this is the second expression here is normalized expression where n minus 1 is actually used to do the way this particular summation. Now, for example, just take this particular example. This is the same example we showed in the previous slide. We have estimated the average path length, the shortest path length from every node. So from node A to node E. Node A to node E can have a shortest path to C, A, C, E. That is a two-post path, two-pop path. Now, for node A, when you look at the shortest path B is 1, shortest path C is 1, E is at 2 hops away, E is also 2 hops away. So you sum up these shortest paths, you will get to sigma j dij, that is 6 for node A. And when you take the closest centrality, 1 over 6, so you will get 1 by 6 as the closest centrality. The centrality of node C here. Node C is 1 hop away to every other node. So the summation of the shortest path will only be 4. So the closest centrality is 1 over 4, that is 0.25. You can find that node C has the highest closest centrality in this network. So that node has a significant advantage of requiring minimum delay and minimum resources to communicate to every other node in the network. Now, in some of the representations, we divide this summed up average path length with n minus 1 because of the division in the denominator, the n minus 1 will come to the numerator. So that way, you will get a value between 0 and 1. Once again, higher value of CC represents the node is more central to the network. Now, similar to the closeness centrality, between the centrality is another very important metric, very influential metric. How between a given node is for the rest of the nodes in the network. So what that means is the extent of a given node and its position path of other nodes in the network. So, for example, you see between the centrality of a given node I can be estimated by this expression E AK of I. So, what this means is for how many shortest paths this node I is present divided by the number of shortest paths between the remaining nodes AK. Okay. Now, what that means is, so a given node is present in several of the shortest paths. Okay. Now let me take one example here. So here you can see node 3 is C here. Node 3 is particular node C here. So C is in the shortest path of E to A, E to E, E to A, E to B, and so on. So XC is in the very shortest path. So we can see that out of the 1, 2, 3, 4, 5 into 4 in the, so out of the several shortest paths, or out of the so out of the several shortest paths, the node C is in 4 of them. Okay. So what that means is the between the centrality of the node C, that is represented as 3 here, is actually 5. Whereas if you consider other not in the shortest path of every other node, D is also not in the shortest path of every other node. Same with the D as well as C. So between the centrality of other nodes are actually 0 in this particular case. So that way, between the centrality plays a very important role in the ability to control the communication across other nodes. Okay, because other nodes communication is passing a given node if that node was high between the centrality. In this case, the entire network's communication is actually passing through 5 out of 6 shortest path will have C passing through it. So C has a significant influence over the communication in this network. Now, similarly, there are graph centrality metrics that of the entire network centrality. So this is taken across segments of graphs to get to the centrality metric. So as I mentioned earlier, degree correlation is one of the important metrics which shows a relationship between a connected node layer 2. So basically what this metric represents is a given node is connecting to other nodes in the network. So how similar or dissimilar are these nodes together? In between the connected node pairs, we have 2 categories, associative and disassociative. So in associative network, a node is likely to be attached with another node with a similar degree. For example, nodes with high degree are likely to be connected to the higher degree nodes. possible node pairs. So, it means the selection of nodes or edges can be actually done by some random generating function. So, for example, you have a total number of links provided. Then an n node network can be constructed by generating a function with a random generating function n, p, n, m. Or alternatively, the probability of link creation is given, where p is the probability of link creation. Then also a random network can be generated or created or even evolved by generated into n comma p, where n is the number of nodes, it is the probability of an edge existing between nodes. And this model is a very popular model known as Erdos-Renyi random network model. Now, this is actually function used to create the Erdos-Renyi random network model. So basically, P is a graph of n nodes, P is a link addition probability, N2 is a group as well as there. And for every node pair, you take a random function with probability p, and then you connect it with that probability p with node I. So you will eventually get what is called a random network or ER network. So the network creation time is for n squared here. Now, this network has been very well studied by the research community, and some of the findings I'll briefly explain here. The expected network size is exactly m links estimated to be P of m, that is NC2 Pm. P power m is the probability of network formation, link formation. M is the number of 1 minus p to the power NC2 minus m. Similarly, the expected number of total number of links given m and p is sigma m 0 through NC2 m p of m p NC2. So, in addition to that, one of the very important estimates is the neighbor degree can be estimated in a random network given the parameters n and p. So, average neighbor degree is close to NP, where n is the number of nodes and p is the probability of link formation. Now, as you say, when p is 0, it's a simple giant component. Now, you can get the size of the giant as well as the probability of value that can actually form the giant component. That is, when p greater than or equal will have a giant component. Now, the network diameter for ER random graphs are estimated as ln of n divided by ln of an average neighbor degree. So, capital N is actually the number of nodes in the network. Small d is actually average neighbor degree. So, very easily we will be able to estimate the statistical properties of ER network. Average path length can be estimated as ln of number of nodes minus epsilon divided by ln of the neighbor degree plus 1 by 2, where epsilon is a replacement parameter. Now, given this kind of a network with the p and n, we'll be able to estimate the clustering coefficient by insertion. Degree distribution is found to be following Poisson distribution with this expression where n minus c combination k times p4k into 1 minus p to the power n minus 1 minus k. So, where the probability of k degrees found can be obtained by this expression. So, we basically will be able to estimate the parameters of random networks very easily once we have the basic network parameters like n and m or n and p of a given ER network. Now, that is one of the well-known models of the network. Now, I'm going to discuss small world networks. So, A regular network is nothing but a structured pattern where a 2D grid network or 3D grid network or a string topology network are all regular structures. In comparison to the regular network, just to discuss the random network, how uncertainties in the formation of the network, uncertainty in the structure appearance of the network. Now we want to compare this regular as well as this random network with this network type called small world network. Now the key point is the characteristics of small world network lies in between regular network and the random network. So let's look at based on the parameters that we have discussed earlier, the average clustering coefficient, average path length, and asymptotical values of average path length. Let's compare regular network, small wave network, and random network. So regular networks have moderate average clustering coefficient. As I mentioned earlier, the clustering coefficient varies between 0 and 1. And 1 means your neighborhood is very well connected. 0 means the neighborhood has absolutely no connectivity among themselves except through you. So that way, depending on the exact regularity, you can have moderate connectivity among your neighborhood. Okay, but the problem with the regular network is the average path length is very high. So the average path length is order of n in a regular network. Okay, so if you a string network or grid network or 3D grid, you have order n as average path length. Now compare that with a random network or random network. So you find that average clustering coefficient is low. So why this average clustering coefficient is low is because you are connected randomly to a faraway node, or your neighbors are also randomly connected to faraway nodes. So your neighborhood does not have connectivity among themselves. So the random networks have low clustering, average clustering coefficient. So neighborhood is not robust in case of a random network. But good thing is the average path length is low. So you can find that the average path length of a random. Now comes a small world network. Small world networks carry the benefits of both regular network as well as random network. Say moderate average clustering coefficient ensures robustness in the network. At the same time, average path length is actually following random networks behavior of law. Okay, so it has law path length. So that's why a small world network can become really important. Now the question is, why a small world network is called a small world network, and what are the insights that we can get from that? So the small world characteristics is first observed in social network studies done in US in 1967 by a scientist called Stanley Milgram. So he actually studied how people are connected among themselves in two cities from Wichita and Omaha. Okay, and he persons known to them by very personal contact. So, what I mean is, for example, if I want to write to, say, for example, the President of India, since I do not know him, I cannot write him. But I am requesting somebody who I know that and personally known to me to forward that. So I must be sending the director of our institute thinking that he must have some personal contact to the President of India. So I'll send my director. But director himself may not have a direct contact with the President of India. So he will actually write to probably chairman ISR or secretary department of space who might be doing personally to him. So that way, through personal contacts, letters were forwarded, large number of letters, and these letters were used to identify the number of hops it took to reach the destination. So, and each recipient was asked to write the names and get that into a log. The logs were collected and analyzed and found that they found the number of hops between people were very small, that varied between 2 and 10, with the median number nearly at 5 hops between random number of people. Okay? So this is why the term called 6 degrees of separation came into existence. So we concluded that even if in a really large population, the number of people, that number of hops with which separation happens between people is a very small number, something like as small as 6. So the paper is actually available in this reference here, Stanley Milgram, the small world column in the Psychology Today, 1967. Okay, so this term has become so popular, and the characteristics that such a large population forming a network can have very small average path length is evident in several such physical situations too. So that is the reason why this network is called small world network, because even though the network is very large, you have order log n path length, which is indicating the network is actually small. Okay. Now, this is the depictions of the experiment that I mentioned. So now, for real world applications, you can actually create a network. Okay, you can create a small world network to benefit the small world characteristics. Now, what are the small world characters that we are going to benefit? Path length reduction, better robustness. Okay. Now, the two most popular ways of creating small world network out of regular network is rewiring existing links or adding new long range links. Okay. Now let's take this particular network. It is a regular network. The regularity is in the kind of organization of links. Let's say a node has uh, uh, one link to immediate neighbors, one pair of links to immediate neighbors, another pair of links to second immediate neighbors. So that way, every node has same structural similarity. So that's why it's called a regular network. So this is called a four regular network because there are four edges originating or ending in every node in the network. So for this particular regular network, the average path length is 1.67 hops and average clustering coefficient is 0.5. Okay. Now you can convert this into a small world network by rewiring. For example, this link between 1 and 2 is cut and taken to a new destination, that is 4. Okay. Similarly, the link between 1 and 10 may be rewired. So from 10 to 6, it has gone in this one. So that way, the dashed links here show the rewired links from the original links. Now, this regular network, through the rewiring process, became a small wave network. Now, the rewiring probability used to show is point is fairly high probability. Usually, people use with small values like 0.1, 0.01, and so on. Now, this rewired small world network has an average path length 1.58 and average clustering coefficient 0.34. So you can find that the average path length is smaller than the regular network here, and the clustering coefficient decreased slightly. So this has not become a random network, but the average clustering coefficient is still a good compared to a random network. So that way, this network, regular network, is transformed into a small world network to get it smaller and with a moderate sized average clustering coefficient. So that way, you can accomplish certain things. So I will show you some experiments conducted and the results obtained in terms of the benefits. Okay, so this is a 100-node network, 4 regular network, and the probability of rewiring is 0.05. And before rewiring, the average path length was 12.88. and once it is reviewed, the average path length when p is 0.05 is only 7.19. Okay. Now, average clustering coefficient percentage reduction, 44 percentage average path length is reduced. So what that means is even if p is very small in a 100 node network, the path length reduction is 44%. The network has become 44% smaller compared to the original regular network. Now, say with take another example. So 500 node network, the average path length is 62%, 62 hops, and even with the speed very small 0.05, 81 percentage reduction in average path length has been achieved, where the after rewiring path length is only 11.68. So significant reduction can be accomplished by small changes to the network structure, even by adding 0.05 probability for rewiring, you will be able to accomplish significantly. Now, so remember the clustering coefficient was 0.5. Clustering coefficient will remain 0.5 irrespective of the number of nodes because of the 4 regularity that we have seen here. So even with the 500 nodes, clustering coefficient is 0.5, and clustering coefficient can decrease a little bit depending on the p value. So with this 0.05 p value, when you get 81% reduction in the average path length, the clustering coefficient has come down only by 0.05. So 0.5 has become now 0.05. So you reduce the path length from 62 to 11.68 on an average. The average clustering coefficient has come down to 0.45 after the original 0.5. So that's why the balance is actually very good. But if the probability value increases from 0.05 to 0.5, then path length benefit is very good. You will get the average path length reduced to just 5 hops in a 500 node network, but clustering coefficient takes a dip to very small value. So what that means is the network slowly becomes like a random network when you increase the p value. When you increase p equal to 1, then the regular network becomes a fully random network or ER network, where you will get log n path length as well as clustering coefficient a very small value. Now, the distribution of degree distribution of small world network. So this is some of the experiments that we have conducted. So when with the p 0.5 through p 0.05 to 0.5, so we were looking at how the degree distribution changes. So we can see that it was a regular network. A regular network has a degree distribution only at single value, that is degree 4, where all the nodes have 4 degree. But with the increasing value of p, it approaches more of a normal distribution or a distribution followed by random networks. So now, as I mentioned earlier, the degree distribution says probability of finding degree k versus degree k. So this is not normalized value, so you will be able to estimate this as 4 degree. There are 200 to 250 nodes with 4 degree. Okay, so when you normalize this, this will become a probability value. Now, some examples of small world networks from real world. So this is actually a friendship network gathered from a study of a German social network. So there are 53 nodes in this and 173 links. So we may not be able to get an idea what kind of a network is this. So that's why we will look at the path length, we will look at the average clustering coefficient, we will look at the degree distribution to characterize what kind of a network is. This is actually coming under the category of a small world network. Again, this is again a social network in the animal world. This is a network of dolphins, 62 dolphins, and their social interactions obtained from a study of a zoo in New Zealand. So, once again, people may not be able to recognize what kind of a network, but quantitatively we can classify this as a small world network. So, this is a network of disease and the corresponding genes, disorders of diseases and the corresponding genes. So, this was 1419 notes and 2738 links. This is another example of a real world small world. So, there are many such examples we can find in the real world that shows the characteristics of a small world network. Now, reason why these are called small world networks is because when you take this network, the number of nodes, the number of edges in the network diameter, the average degree, average path length, and average clustering coefficient. So, when we look at the average path length and average clustering coefficient, you may be able to find it closer to log n and moderate size of average clustering coefficient, then you will be able to characterize this network as a small world network. So we can find that log n comes about 3.97. The average path length in this network is 3.38. So that way we will be able to identify and characterize the network based on the average neighbor degree, average diameter, average path length, and average clustering coefficient in this particular category. Now let's look at a few models based on it. I will very quickly cover this part as it will cover which take a lot of time. I have mentioned earlier how to create. One is based on the rewiring or addition. But there have been a lot of work on this, on how to create a small world network for different categories of network. So, a few selected work I'll briefly explain. But we can classify the entire set as three possible ways. One is random decision based network model, or random decision is applied to get a regular network into a small world network. Second is a deterministic decision. Deterministic decision is actually you have a very clear deterministic value-based decision or deterministic policy-based decision that will actually convert a regular network into small world network. A third is applying a heuristics, okay, simple heuristics that can work well. And in many cases, heuristics are very useful and getting very interesting properties of a network. Okay. Now, let's very quickly look at these examples. So, as I mentioned earlier, rewiring possibilities. You have a regular network here with the P as a rewiring possibility. You will be able to get a network in a small world network. When P is between 0 and 1, you get a small world network. When P approaches 1, you get a random network out of this regular network. Now, actually add a link to get it, especially in wireless like network. You cannot rewire a network because you cannot terminate a wireless link from your neighbor and connect that to the farther away node that easily because of the broadcast nature of wireless links. So in that case, you can actually add a new link in addition to the existing link. So now one possibility is to have a new link added randomly, some value P. So basically, for all the nodes, you will make a long link addition by a random decision within the network. So this is actually very simple. For adding k links, you only need to some complexity of order k to make it a random for each small world network. So this is an example for a simple string topology network. So this is a 40-node string topology network, a regular network, where you randomly pick one node pair to add a long link, say LL1. Then you have actually reduced the path length to 10.58 and neighbor degree should be after addition of this LL1. Okay. Now, uh, uh, second stage, you added one more long link by again random decision. So you reduce the average path length further to 8.13. Third stage, you fourth stage, fifth stage, and after several stages, you will be able to add maybe several links. Maybe 6 links are added, 6 long links are added. So this network becomes a small world network by pure random decision-based addition of a small number of long links over this network topology of 40 nodes. Now, if you see the degree distribution of the nodes, that network that we have randomized, we can say that this is a semi-log scale where probability of finding a degree and this is actual degree. Say degree 1, 10 and 100 in 10 to 50 node network. So we can find that the degree distribution follows the Poisson distribution approximately. Now, asymptotic value of is found in this network. It incorporates small well probability. Now, one of the very novel theoretically proven model for creating a long link is called the Plainberg's model. So, this Plainberg's model adds new links with a probability function that is inversely proportional to the distance between nodes. Say, what that means is, if you have a grid network where there are two nodes U and V, the distance between the two nodes U and V is D, then the probability of adding a long link between these two nodes U and V will be obtained by this particular function, DUV to the power minus alpha divided by summation of all UV. So what this referring to is 1 by distance to the power alpha. So what means as the distance is increasing, you will find the probability increasing for addition of long links, which means you have higher probability of adding nodes in neighborhood, but lower and lower probability of adding nodes and further nodes within the network. Now, when Plainberg's paper is actually having this particular reference, which appeared in Nature in 2000. The important thing is the factor alpha can have a very important characteristics when it is true, where you will be able to find optimal and low time complexity solution. So that means when the probability value is inverse square of the distance, then that network has very interesting properties such as very low time complexity to route and find the paths in the network. Now, as I mentioned earlier, you can add using deterministic link additions where you can go for optimal or suboptimal deterministic functions that can be used to add links. So one of the solution is optimal long range link addition or optimal LL addition within a network. So the algorithm is very simple to write, but it is very complex to add. So basically, for adding k links, you need to find which is optimal addition point within the network that can bring the APL value to the lowest possible value in the network. So this is having high time complexity. The time complexity is adding optimal long length is n power 2k plus 2 log n for adding k long links within the network of n nodes. So it's not really suitable for large size network. Now, so because the optimality is very complex, through exhaustive search, people go for near optimal or suboptimal solutions. So this is actually one of the algorithms for adding near optimal long range link additions in network ticket. So the algorithm is very simple. I'll just very quickly explain that. So for adding k links, you take a loop for 1 to k and ith LL is to be added. So now this ith LL is added based on APL of addition of this link over every pair of nodes. Okay, which means that the network will compute APLs if this ith link is added to every possible pair and find the pair where the addition makes the lowest APL. Okay, now then if there are multiple such solutions, then randomly pick one solution and go ahead with it. So this near optimal solution, once again repeat what is the strategy. For the first LL to be added, you will compute which node pair is the best to be the choice of long link addition so that the A pair is actually lowest in the network. And you add that. Then you go for the second link addition. And again for the second link addition, you compute where is position or which node pair can be chosen to add so that you will get the lowest APL in the network and you add it there. So the time complexity of this near optimal addition is k into n power 4 log n. Compared to this time complexity, this is much complex, but it is now in polynomial time now. Now, example of that is here. For example, now just for the previous case of link addition, now we try to add this long for this link addition such that the APL is actually lowest. Now, if you look at the previous example, the first long link was added randomly here. So the random decision may be between 18 and 27. But when you look at all the pairs where this link addition makes sense, we found between 8 and 32, you can actually add this long link 1. So it will bring the APL to the lowest possible in this given network. And LL1 is added, which gives lowest APL. Now LL2, the second long link is to be added. Again, it computes all combinations where this LL2 can be added and finds LL2 can be added between 20 and 32 where the APL is lowest, that is 6.75. And so on, it goes to k steps. At every step, it computes all possibilities and finds the lowest pair, and eventually the network comes in this particular line. You can find that one node here, the node at 32 in this 1 through 40 node emerges as a important node with several links coming to it. So that becomes a hub node in the network. Now, we have actually obtained a theoretical analysis of this by following a dense string graph, and we found that the positions, optimal positions, have something like a 80-20 rule, okay, in a string topology network, where if you add a long link for the first LL at 20% and 80%, that actually becomes the lowest APL. So what that means is, if you consider a ring topology network, a regular network, if you want to add one long link, you can actually add it across the, across the diameter of the ring, where you may add 0.75 n to 0.25 n or 1 n to n by 2, something like that, to get the optimal location of the first long link, which can bring down the average path length to the lowest step. But when you have a string topology like that we have shown in the previous slide, you do not have a complete string. You may have 1 to n nodes. Then the optimal link position shifts to 0.2 and 0.8, and there's only one unique position to add this. And this unique position at 0.2 n and 0.8 n are called anchor points, because that's the points where when you add a single link, that brings a network APL to the lowest possible value in the network. Now, surprising to find that this link addition balances the average path length contributions of each segment. Now, when you have a 20 node network, the anchor points are node 4 and node 16, and the path contribution of 1 through point to n and the path length contribution of 0.8 to n, sum of these two path lengths is exactly matching or roughly matching the path length contribution of the inside node here. So if you look at different node sizes, the path length experienced by various these three segments, 1 through n has a path length, sum of path lengths will be 660. Whereas 0.8 to n also has sum of path length 660, and the segment that is at the middle has a path length experience of 1340. So sum of this segment path length plus sum of this segment path length would be equal to this segment path length to get these anchor nodes corrected. Now, what that means is there is an existence of a unique path, unique points for a string topology network where one rounding can be added to optimum to achieve optimum or maximum reduction in average path length. Okay, so that is one way a network, a string topology network can very quickly converted to a small world network with all benefits that a small world networks come with. Now, there are many other ways of adding deterministic approach to get a network into a small world network. So this is a network where you can grow nodes using a pattern where the leaf of the nodes are connected. So, for example, usually the network is at time t is equal to 1, the network is a 3-node network. One is a root and the two nodes are the children. Now, these nodes are replicated and the leaves are connected. And if you grow a network like that, as you see here, eventually you will get what is it? Now, let me just skip a few slides here. I want to mention that the small world networks can have significant other benefits too. Before our time is up, I'll just cover the important type of network called scale network too. So let me just skip a few slides here. Okay. Now, so I have mentioned earlier degree distribution, which actually goes as an important metric for evaluation of the network. So now I want to compare this network type called scale-free network with a regular, small world, and random network. Okay, in terms of AC, ACC, APL, and asymptotic APL values. Okay, now we have seen that while small world networks have moderate ACC compared to regular and random network, scale-free networks, it's the new category of network, follows a power law degree distribution to have low average clustering coefficient. Low average coefficient is not necessarily be a good characteristic, but it actually follows similar to a random network. Now, average path length is very small for very small, extremely low for scale-free network compared to small world network. Okay, typically the average path length can be order log n. So some people use the term ultra small world for scale-free network. So let's see what is this network and how is this characteristics. Okay. Now, the degree distribution characteristics of small world network is power law degree distribution, where probability of a degree is inversely proportional to d power gamma, where gamma represents the slope of the distribution curve. Now, this distribution is having a slope that is constant irrespective of the size of the network. So what that means is the distribution does not change with the size of the network. That's why it's called scale-free. For any size of the network, this characteristics of degree distribution can remain there. So that way the network is actually having important properties. So one property is called it has hub nodes. Many nodes that have large degree can present in this. It also has small world properties, but sometimes it's called ultra small world because of the order log n path length. Now, network diameter is very small, okay, and it has a degree distribution power law. Now, let's show some pictures. This is a normal distribution. This is a power law distribution. When we say this is a log scale, the power law degree distribution is represented as a straight line where the slope is actually scaling factor. In this case, the scaling factor is 2.5. Now, the reason why this network becomes very important is because many real-world networks are categorized as scale-free networks. So this is a protein-protein biochemical interaction network with the 2,361 nodes and 718. So this network is having an average path length of only 4.65. Okay, even though this you cannot see that from the picture, even though the number of nodes is so high, the path length is very small. And another network, over-citation network. So you can see that your paper cites another paper, maybe another dozen papers, and some of those papers will be cited by other papers too. So that network of which who cites who, or which paper cites which other papers is represented as a network here. And so this network is also found to be a scale-free network. Computers in the internet, the autonomous systems in the internet, that is also found to be a scale-free network. Now, the question is how to calculate, how to estimate a network as a small world or scale-free is to be done by this particular example. So I have just collected some examples from the real world. The social network called Karate Club network, World Trade Network, World Adjacency Network, American Football Network, and so on. You can find that some of these networks have the number of nodes very high. For example, network of autonomous systems in the internet, 22,960 nodes, and the number of edges will be 48,000. Even Marvel University characters actor network, 10,000 nodes or 1,78,000 edges. The Twitter call network, thousands of nodes and lakhs of edges. And you can see very large number of nodes and edges exist in this, but the network diameter can be much smaller. So you can see for this particular network, the protein-protein interaction network with the 2,361 node, the average path length is 3.04, average clustering coefficient is 0.07. So the co-ownership network has an average path length of 3.45 and average clustering coefficient of 0.88. Now when you look at this, the average path length is closer to log n than log n. And the average clustering coefficient can be very small too. So that is one way to categorize, in addition to finding the degree distribution of this network, to see whether this network has small world characteristics or scale-free characteristics. In all these cases, we can find that the average path length is closer to log n compared to log n in many of these star networks. Now, I'll just show one or two examples of how scale-free network can be formed before we close. So many ways people have studied scale-free network formations because of its natural existence in various forms. One is preferential attachment-based model, node fitness-based model, intrinsic fitness-based model, optimization-based network creation, and scale-free network with exponent 1, greedy global decision-based network model. There are so many models. I have references for all these network models. So one way is actually to add nodes with the probability that is taken with the degree distribution. So, for example, you are actually joining a network, an existing network, but who is your immediate neighbors when you join that? If you take that decision based on the neighbor degree of the existing network nodes, then you are likely to join with the richest node in the network or the most powerful node in the neighbor degree in the network. Then you will eventually create a scale-free network. So this is a theoretical model of how it can be created mathematically or growing a network. That's called preferential attachment model. So, pictorial example I can explain very quickly. This is an existing network, and you are actually creating new edges. When you create a new edge between this node and the other nodes, you try to look at which are the higher probable nodes. And this node has 3 degrees. This node also has 3 degrees. This node has only 1 degree. So there is a higher probability of choosing a node with higher degree. So you might be choosing this node or this node. And if you choose a node with higher degree as your neighbor for adding a new edge, then you will eventually create a network with the scale-free characteristics. So scale-free characteristics is very real, possibly real world situations. So I don't know to explain everything, but one decision, greedy, global, LL addition is a possible way to do that. As I mentioned, they are here adding LLs in a network where global optimization is considered for every link addition. Then at the end of the day, you will actually get what is called a degree distribution that follows power law, where the gamma values are there around 1.8. So that is one another possibility. I have explained for the scale-free network where you connect with the leaves. But if you alternatively connect with the root and the leaves of the new segment of nodes, then you will actually get a scale-free network, not a small world network. So that way, this is the exact opposite of the Delna network creation process, where you will end up getting a scale-free network. You can see that here the network of 3 nodes with 1 root and 2 children are replicated, but the root of this network, this segment, is connected to the leaves of the newly created segments. Now, the degree distribution of this node increases. Degree centrality of this node increases, and with every node growing, the degree centrality increases, and it creates a so I'm a network and scale-free network. So, in fact, there are a lot of open research issues on these areas. One is what is the reason for scale-free network creation in many of the real-world networks? How do we find the optimal location of hub nodes in a scale-free network? Or how do we identify a network clearly a quantified way as a small world or scale-free network? We still use some of the references or inferences like APL, degree distribution to get it, but it's not easy to quantify every network into one of these categories. Efficient routing protocols for scale-free network design or any other cases. So community identification also. Let me stop with this for any reference. Just and as I mentioned earlier, this was actually part of material from our recently published textbook called Complex Networks. We have 2 parts, a networking perspective and a signal processing perspective. And in the networking perspective, we had we have many topics such as I mentioned earlier, how to use small world for wireless networks, how to use small well for wireless sensor networks and so on. On particular how to modify the network to get certain benefits from the small well, scale and other network characteristics. So then it also has signal processing applications where graph signal processing concepts are actually discussed. How do you represent the graph with the signal processing information and how to process that? What is this important characteristics? Scale-free networks, small well networks, and so on. So this was right part. So let me stop here. If you have any questions, I'll be glad to take that. You can also email me at the email address @iqt.org. You may exceed the time. I was told 10:30. Sorry.
Sir, there is a question
Yeah, please.
in chat box, sir.
Yeah.
How graph theory and complex networks are related?
Yeah. Okay. So they are very, very closely related. Graph theory is relevant when you have finite sized networks. Okay. When you take the statistical properties of a graph that is required for complex network analysis. Okay. Now, when you say average path length, that is very popularly used for graph theory studies. Okay. Same with average clustering also. But when you take the distribution of nodes, probability related factors of a graph, and the number of nodes becomes too huge, and you cannot make a real sense of how the structural properties of a graph is. That comes under the category of complex networks. So that way, graph theory is preliminaries of complex networks analysis. Is that clear, or you want me to give some more explanation on that?
Sir, another one question, sir.
Okay.
Hello.
Yeah.
What about the performances of these complex networks?
Yeah, performance of depending upon certain specific metrics. For example, in this particular case, we have the structural properties to characterize the network into random. Small well, this is actually performance metric. But when you look at network performance in the computer networks, like the throughput, delay, and other factors, plays a major role in the throughput, in the end-to-end delay or delay experienced in the communication. Of course, it brings in additional factors like the traffic load, loss, the media access control protocols, contention-related factors, and so on in deciding what is the end-to-end delay. But path length plays a major role. So in that case, if you have a network, say let's take a small world wireless mesh network, you have a network with the path length on an average 10 hops. So this 10 hops is going to play a major role in the end-to-end delay that you are going to experience in the network. Now you modify the network to make it smaller, say 6 hops. Now the path length has come down, so the end-to-end delay is likely to be lower for that smaller network. So that way you can actually improve the network performance by making structural properties changes by making into small weld or scale plate. If you make a network more smaller by making it a scale-free network, obviously your average path length will be much better. What happens is there will be nodes that are called subnodes that will be formed. These subnodes are likely to face higher contention in their channels. And if you can handle the traffic there, then the throughput performance will be very good there. But if you cannot handle the traffic in those subnodes, then the throughput will suffer. So there is a trade-off in using the average path length of scale-free networks when you design actual physical wireless or wired networks. To provide sufficient resources to the hub node, the network is going to have significant performance. Now, another angle of this, I have mentioned about the end-to-end throughput, end-to-end latency or delay, and how small world networks can improve. Scale-free networks also can improve, provided the hub nodes have sufficient amount of resources. Now, alternatively, security is another thing. So, if you have the hub nodes in the scale-free network, then they are highly likely to be under attack because of their importance in the network. A central node or a hub node will be guiding a lot of traffic within the network. So if we can potentially attack that node and destabilize it, obviously the network will get disturbed more. So that way, small world is actually better because there is much less number of central nodes in a small world network, which provides somewhat lower path length compared to a scale-free network where the hub nodes are very few nodes. Yeah, if you have any other performance-related questions, I can mention, but the structural properties make a significant impact in the performance of network in terms of throughput, delay, earlier, small world network can play a major role in the trade-off between path length and robustness. If we go for scale-free, robustness will suffer, path length will be benefiting. Okay, but if you go for regular network, robustness will be better, but path length will be suffering. The small world can give a trade-off between these two categories: extreme robustness to extreme smallness, so that the network can actually work somewhere in between. So, yeah, many of these real characteristics like the throughput, delay, robustness, all this can actually be influenced positively by making structural changes to the network. Thereby, we will be able to get it.
Any other questions?
Hello? No, I could not hear you well. Please repeat that question.
Okay, sir. The participants have given feedback, sir. It was a use session.
Yeah.
The session were
Okay.
so
No? Yeah. Okay.
sir, informative, useful. Sir, it was very
Yeah. Okay. Thank you. Thank you very much. I'm glad to
so on behalf of compliance and engineering, sir, on behalf of Department of
Okay. Yeah. Yeah. Yes, I can hear.
and Manoj sparing time with us, sir, to really grace our internet. Is it audible? No? Is audible, sir? Hello? Okay, sir. Okay, sir. On behalf of Department of Computer Science and Engineering and Organizing Committee. Okay, sir. Thank you, sir. Thank you, sir. Thank you, sir. Thank you. Okay. Thank you, sir. Thank you, sir. Thank you, sir.